So I have sprinkled through many of your previous lessons. Nicole, can you go back to your desk, please? I've sprinkled through many of your previous lessons, applications of exponentials. Mostly that was just review. However, I did introduce 3 new grade 12 function notation formulas to you. They are really the same as y equals a times b to the x that we learned in grade 11. They're just slightly different notation, and they're organized so that you have like something for percent growth, something for percent decay, half-life, or a doubling already entered into the formula for you. So these 3 formulas, I'm not going to reintroduce these today, but there are some questions 1 to 8, that will do exponential, like a recap of exponential stuff that you can work on. I'm going to introduce 3 new formulas to you today, the logarithmic formulas, for applications of logarithms. Okay, so that's just what we're going to go over today. So the first application of logarithms is pH. And many of you guys have probably seen this in your chemistry classes if you take chemistry. And the pH, for those of you that aren't into chemistry, just basically measures how acidic or how basic a chemical solution is. So you've got sort of like a chart over here that kind of gives you a range for different types of pHs and their different acidity and alkalinity. When we have something in the middle, that would be considered like a neutral solution. So something like water, or like the things that are close to that would be blood, water, and milk. But pure water would be neutral. It's neither acidic nor basic. Okay, so logarithms with base 10 are useful when we calculate pHs because the entire pH system is based on a base 10 system. And basically what we're saying is if something has a pH of 8, the reason why we see it has a pH of 8 is because the concentration of hydronium ions is 10 to the negative 8 moles per liter in that specific solution. So the amount of hydronium ions is going to determine whether our solution is acidic or basic. And that is actually what the pH scale does for us. Okay? So maybe we know from chemistry, like if I say the pH is 12, I know that's a very, very basic solution. It's high alkalinity. But maybe we didn't know that that means that, or hopefully you did know, but maybe you didn't. Hopefully you know that that means that it's 10 to the negative 12 concentration of hydronium ions in moles per liter for that solution. Okay, so here's our formula. The pH of a solution should be equal to the negative log. Remember, this is base 10 log. That makes sense because it's a base 10 system. Of this H plus represents the concentration of hydronium ions. So let's take a look at an example here. A toilet bowl cleaner has a hydronium ion concentration of approximately 0.1 moles per liter. What is its pH? So I'm simply going to enter in the hydronium ion concentration into my formula. And then I can just calculate on my calculator. What is the pH? Athena? pH should be 1. Okay, so obviously that tells us that our solution is very, very acidic. So far, so good? Not too bad, right, Esther? Okay. Egg white has a hydronium ion concentration of approximately 1.585 times 10 to the negative 8 moles per liter. Is egg white acidic or alkaline? Let's plug this in. Again, this is concentration of hydronium ions. So I'm plugging this in to the logarithm here. What you might want to do is just calculate that first and then plug it in, say log of answer times by negative 1. Or you could just plug it in all at once. Probably would still work. Oscar? Yeah, and we can see that on the chart here. Eggs are slightly basic. Okay, Okay, so just make sure you can get that answer in your calculator. The reason why we use stuff like 10 times -8 is because when I multiply something by 10 times -8, I'm saying we need to move the decimal over a bunch. So it's easier to write times 10 to the -8 than it is 0.00000 something, right? So that's why we have notations like that. Okay, here's a third pH type question. So I can be given the hydronium ion concentration, or I can just be given the pH and be asked for the hydronium ion concentration. So lemon juice has a pH of approximately 2.2. What's the concentration of hydronium ions in lemon juice? So I'm going to sub that in for the pH this time. And then our job is to isolate for the hydronium ion concentration. So before I switch this into exponential form, I'm actually going to divide out this negative. So it'll be negative 2.2 equals the log of the hydronium ion concentration. And this is base 10, right? So if this is base 10, how do I switch this into exponential form? Oscar? Or sorry, I meant Oliver. Did it again. Yeah. My chemistry people, maybe you can tell me, do you guys always express it with the square brackets around it, or are there no square brackets? Okay, so we'll keep the square brackets. Okay. Okay, and then if we wanted to, we could calculate this. I don't think it would be that tough to express this in, your calculator gives you out like a nicer form of this, which will be like 6.3, we can say 6.30, I guess we'll do 10, 6.31 times 10 to the -3. Okay, but we do know, I would be fine as well, like, I mean, technically, you should express it in this format, but if you happen to give me this answer, I'm not going to make like a big deal about it. And this is moles per liter, so I'm going to add that as well. Okay, so this is a flip into exponential form. If you understand the pH system, then you probably also understand that if the pH is 2.2, it means you have 10 to the -2.2 as your concentration of hydronium ions. So you could really just go right here. Okay, decibel scale. The decibel scale is also a base 10 system, and what it does with our formula here is it can compare the intensity of two sounds. So here is a chart of some common sounds that might be around us. Hopefully some of them are not around us on any given day. But we have low decibel levels like the rustle of leaves or a whisper, 10 decibels, 30 decibels. Normal conversation, 60 decibels, and so on. Once we get to the top, we have things like that could be potentially fatal, like a rocket taking off if we're right next to that, a jet engine. Rock concert speaker is 150 decibels. So that just gives you sort of a range of reference there. Here's our formula. B2 minus B1 is the comparison of two sound levels in decibels. And then I1 over I2 is the ratio of their intensities. And intensity, the unit of measurement for this is watts per meter squared. So let's look at some examples for decibels. How many times as intense as the rustle of leaves is the sound of a shout? So we're going to refer to our chart over here. The rustle of leaves from our chart is 10 decibels. And the sound of a shout from our chart here is 80 decibels. And we are just going to isolate for the ratio of the intensities. So I'm not trying to solve for I1 or I2. I'm actually just trying to solve for the whole I1 over I2. So I'm going to call this, this is what we call beta. Looks like a B. Beta 1, beta 2. I make the more intense thing or the higher thing beta 2 because we're going to compare how much louder the louder thing is than the quieter thing. So let's plug this into our formula above. Beta 2 minus beta 1 should be equal to 10 times the log of the intensity of sound 2 over the intensity of sound 1. These should be matching things, right? The intensity of sound 2 should match with beta 2. The intensity of, oops, sorry, this should be 1. Don't know why I put a 2 there. The intensity of beta 1 goes along with the intensity of beta 2. Or okay, so 80 minus 10 should be equal to 10 log of I2 over I1. Again, I'm just looking for the comparison between the intensities, so I'm actually just going to isolate for this entire thing. I don't need to solve for one or the other, I just want to solve for the whole difference of the intensities. So here I have 70. I'm also going to take a step here, and I'm going to divide this 10 out. So there's not a lot I can do with that until I divide it out. Okay, so this means I have 7 equals the log of intensity 2 over intensity 1. And I just want to isolate for this whole thing. That's what I want to solve for. So how do I get that out of the logarithm? Athena? Switch to exponential form. So this is base 10. It is 10 to the exponent 7 equals I2 over I1. So if I calculate this, this is 10 million, right? 10 to the 7. That'll have 7 zeros, 10 million. So then I can say, therefore, a shout is 10 million times more intense, or as intense, as the rustle of leaves. Okay, so basically just same kind of solving processes that we've been using with all of our other types of logarithm questions. Okay, the sound level of Niagara Falls is approximately 90 decibels. The sound level of an emergency vehicle siren is about 316 times as intense as that. What is the sound level of an emergency vehicle siren in decibels? So this is actually giving me I2 over I1. It's giving me the comparison of how many times more intense the emergency vehicle is when compared to Niagara Falls. So that whole fraction, I2 divided by I1, that's going to be 316 times more intense. I'm going to let the more intense thing, because this is a whole number, that means I must have divided something that was more intense over something that was less intense. So that means that my more intense thing should be I2, my less intense thing should be I1 if this answer is a whole number, right? If I had put something that was more intense as I1 and something that was less intense as I2, I would have had a decimal, right? That's less than 1. So I'm going to make beta 2. This will be the question mark because we're trying to find the emergency vehicle level. And I'm going to make beta 1 the less intense sound, which will be 90 decibels. And then we're just going to plug it all into the formula. So we'll have beta 2 minus beta 1 is equal to 10 times the log of I2 over I1, which we decided was 316. And all I need to do to get beta 2 is just calculate this whole thing and move the 90 over to the other side. So it'll be log of 316 times 10, and then you're going to add 90 to that answer. So how loud is the emergency vehicle siren? Sophia? That's okay. Did you get the same thing, Oscar? So could we maybe just say 115 decibels? So therefore, an emergency siren is about 115 decibels. So you have to use your common sense in these types of questions, guys. If I get something that is not a number that's greater than 1 for the intensity, then I must have divided something that was less intense over something that was more intense. So that's going to help you decide what to put in for beta 2 and what goes in for beta 1. Also, if you just complete the question and your answer doesn't really make sense with what the question's asking, maybe just switch beta 1 and beta 2. So you can always fix it if it doesn't. Use your common sense at the end. This should be the louder thing, the emergency siren, and this should be the quieter thing, 90 decibels for Niagara Falls. Any questions on this one? Okay, last one, Richter scale. So the Richter scale is used to measure the intensity of an earthquake, and the Richter scale is also a base 10 system. So you can see over here, here's all the different levels of the earthquakes. And if we have something 0 to 2, those are minor earthquakes, or micro earthquakes, I should say, happening all the time around us. We don't feel it at all. This would be an epic, catastrophic earthquake. Hopefully, we never see this in our lifetime, because our lifetime will end if we see it. This would be like end of humankind, that type of thing. So we have a formula that compares the magnitude of the earthquake measured on the Richter scale with the intensities of earthquakes. I can also have a formula, like a version of this, like the one above, where I compare the magnitudes of 2 earthquakes. So if I have to compare, I'm going to just use M2 minus M1, and that will be the log of intensity 2 over intensity 1, where I compare the intensities of the earthquake. So this will just be if I want information about a single earthquake. This will be to compare 2 earthquakes. Okay, so how many times as intense as a standard earthquake is an earthquake measuring 4.1? So this actually tells us this I over I naught, or I initial, is what all earthquakes are compared to. So standard lowest level earthquake that we can't feel, we would consider that as like magnitude of 0, right? So when I'm just comparing to like a standard low level earthquake, I just use the single earthquake formula. And I'm going to plug in 4.1 for the magnitude in that. And then my job really is just to isolate for this entire I over I naught. So I just want to know how many more times intense is one than the other. So I don't need to isolate for either of those intensities. I just want to know the ratio of the intensities. So if this is base 10, we're just going to switch this into exponential form. 10 to the 4.1 equals I over I initial, comparing it to the intensity of a standard low-level earthquake. And then I'll just calculate. So 10 to the 4.1. We'll round a little bit here. About 12,589.25. So an earthquake measuring 4.1 on the Richter scale is going to be about 12,589.25 times as intense as what we compare it to, which is like magnitude of 0, like the smallest micro level earthquake. So therefore, an earthquake of magnitude 4.1 is 12,589.25 times more intense than a standard low-level earthquake. Okay, and then the reverse question of this is, if I have the ratio of the intensities, I should also be able to find the magnitude. So what is the magnitude of an earthquake? 100 times as intense as your standard low-level earthquake. So that's giving me the ratio of I over I initial that we compared to. So this is giving me the ratio is equal to 100. I find the magnitude. So let's plug that into our formula here. It'll just be the log of 100. Very straightforward. What's the log of 100? I don't need to use my calculator for this. I don't want to see people typing that into their calculator. 10 to what exponent? Oscar? 2. Okay, so the magnitude would be, it would measure 2 on the Richter scale. So an earthquake that is 100 times as intense as a standard low-level earthquake. Measures 2 on the Richter scale. Okay. If I needed to compare 2 earthquakes, I'm just using this formula where I subtract the magnitudes of the earthquake. So if I want to compare magnitude of 7 to magnitude of 4, let's say, I'll do 7 minus 4 here, and then I just isolate for the intensities. Or if it tells me the intensities and it tells me one earthquake, then we solve for the other one, similar to what we did in part B here. Okay, any questions on these? Okay, so I will give you guys, when you do a test for this unit, I will give you guys these and these. I will not give you the descriptions, so you won't have any of these. You need to know what each of these formulas is used for and what the variables represent in those formulas. Okay, this is what you'll be given. That's pretty much it on the test. So you need to know your log rules well enough. I'm not going to make you write out a formula for the log rules or anything like that, but you need to know your log rules